while looking at space science and what going to be the national contribution in this sector to the whole of the world. All of us know the major components of space research. The space research need not happen from space alone, it can happen from Earth also, and we can also happen in your computer by modeling, analysis, observation. And this has been complementary basically. So we look at the Earth-based observation from the instruments that we have. We look at the complementary instruments that are placed in the orbit. We also look at exploratory missions. We go in situ measurements, remote sensing measurements, the simulation tests that we do in laboratory, and also ultimately bringing about a model and then making some sense out of it as the model-based outcome. Today, the new tools like the AI has come in a big manner for you to help into the space research. I think all of these are going to be supportive of the sector, and many of you become expert in such domains. And in the community that I am talking about, what is represented here, we are blessed with various institutions that are there, created at various time frames in this history of this country. Our scientific institutions look at space as one of their domain. And also we have academic institutions who are creating the talent pool for working in this through various schemes like the undergraduate and postgraduate and research studies. And even in private institutions today that we see a greater enthusiasm to work in space sector and their domains. And even the tools that we have today is actually increasing substantially for us to do this work of research, data analytics much faster and reach conclusions. So the rate of growth of space science is actually accelerated by all of this in the present ecosystem. But we need to do more. Let us look at that part later. If you look at what we have been doing in ISRO in the past, it all started by sounding the atmosphere during the formative years, because there were certain observations that are very important for those scientists at that time, like Sarabhai and others. And the work started at various institutions in looking at the upper atmosphere phenomena, measurements, balloon-based instruments, sounding rocket-based instruments, and how to build them in this country and make a part of the international collaboration. Then we looked at how to build some instruments to put in spacecrafts, and all of the satellite building and launching them through various external launches happened. And slowly the instruments building and building within our launcher and satellite building capacity has happened. But it all happened in a very slow pace, I must say, because of the narrative that we created at the time. The space sector was not really for science, that we did not create, though it actually the whole organization came for building the space science ecosystem, but slowly changed into an application domain where the benefits of space sector to the society and the public became the larger context on which the whole ecosystem was built. So we had to turn that whole narrative in that direction that enabled the whole system to grow in terms of investment and capacity. And once that happened, we are now looking at how to do more science and more experiments and more exploration based on the capacity that you have developed in terms of launching heavier payloads, launching bigger instruments, and making greater outcome out of it. And that's the result that you can see from satellites like the AstroSats, which is one of the very important scientific mission that we have ever accomplished. Then the Chandrayaan 1, 2 and 3, the Mars orbiter mission, and many others that happened, even including Aditya L1. I think all this could happen because there has been a growth of many diverging paths of the launcher capability, the technology capability, the manpower, the human capital. All of this happened progressively. So today we are at a level that we are looking at the long-term vision of the space, and that part will come a little later. Now we mentioned about the various domains of space science work in the domain of observation, simulation and modeling, and also on the astronomy side, astrophysics side, looking at exosolar planets, heliophysics, space weather, study of solar system and related exploration of objects of that type, near Earth space aeronomy. I think all these are being debated, and we have quite a bit of proposals and science aspects right now being discussed. Today also we have the Gaganyaan program where human beings are going to be part of this whole exercise, and we are going to build space stations and put humans in loop in type of experiments, and we have a greater opportunity now to conduct experiments in space, do measurements interactively with the human beings there, and then build and bring back those measurements back to home for better science. I think all these are going to happen in the days to come. Quickly on the type of work that we did in the past, Chandrayaan 1, 2 and 3 are well known to all of you. And the Chandrayaan 1 mission was very unique because at that point in time, our launcher capability was extremely less. The PSLV was the only rocket available. And we wanted to do this mission, and it has to be only an orbital mission. There was no possibility of sending any lander on the moon. And it has to be a remote sensing mission having significant science content. And that's why the Chandrayaan 1 had many of the instruments from other laboratories and institutions. But we also had a moon impact probe that all of you know. And the Chandrayaan 2 came out of various iterations and combinations of such a mission to bring finally a lander, an Indian-made lander and Indian-made instruments as part of this mission using a rocket that was just getting ready at that point in time, the GSLV Mark III. So we could actually do this mission with a payload capability near around 4 tons to do the orbital mission around moon and then make a landing attempt. And finally the Chandrayaan 3 that happened recently has resulted in a soft landing. I think all of this we will discuss a little later. But the bigger impact that has been created by the Chandrayaan 1 is still echoing in the minds of everybody, because the point of the idea of moon impact probe and the measurements that it actually did during the descent phase has been very historic. And this is the first object that we have placed on the south pole, near the south pole of moon. Any man-made object ever to land on the southern side of the moon was the MIP. I think that is something that we must all be proud of. Created by the idea of Dr. APJ Abdul Kalam. I think many of you know it. Which was done in a very short time and worked very well. And the Mars Orbiter mission, which is again accomplished using a lower launcher capacity like the PSLV, and still could do a mission going up to Mars and then orbiting it. And not only that, it orbited Mars for a very long time, it actually produced substantial measurements and observations out of that mission. It worked till last few months back that it has been decommissioned. It worked almost 8 years, though its original life was less than a year, I think. So we have done fantastic space missions with a very limited budget and capability. I think this is something that we must all be very proud of. And of course, all of you know the AstroSat. It is the first of the astronomy observatory, one of the very unique one with a very large spectral capability, and it also produced substantial science outcome. Maybe subsequent talks and sessions will definitely talk about this. The XPOSat, which is recently launched, is the first of the X-ray polarimeter observatory, and this will be the second one, and it gives the more insight into the astrophysical process of black holes, X-ray pulsars, neutron stars, and other luminous X-ray sources. And Aditya L1, and this is the first of the dedicated solar observatory that we are placing around the Lagrangian point, and it has a suite of 7 instruments which looks at the coronal mass ejection, the particle measurements, the X-ray, low energy and high energy X-rays, as well as magnetic environment in that intersolar Earth region. And this has produced very good measurements, and it is currently under the calibration phase, and we look forward to many of the measurements from this in the coming days. Going back to the science outcome of the Chandrayaan mission and also the instruments that are on board, I think let us quickly look at the type of instruments. And in the Chandrayaan 1, we must be very proud that we had a very large number of instruments sourced from various European, Indo-European as well as American sources, and also the Indian laboratories. While we went to Chandrayaan 2, we had most of the instruments coming from India itself, and in Chandrayaan 3 as well. And in the Chandrayaan 1 and 2, we had the remote sensing observations in various areas which will come later. And the Chandrayaan 3 is very specifically important because we are getting the first time opportunity to do the in situ measurements. In various areas which will come later. And the Chandrayaan 3 is very specifically important because we are getting the first time opportunity to do the in situ measurements, which has been done using our remote sensing observations. For example, the first discovery of water, hydroxyl molecules on the surface of the moon has ever been done by our earlier instruments, including Chandrayaan 1, corroborated by the further measurements in Chandrayaan 2, and of course will be with the Chandrayaan 3, I believe. And publications are yet to happen. Moon impact probe is what I mentioned, which impacted on the surface of the moon on 14th of November 2008. It has been a historic event. And you know the location where it is impacted, it is very close to the South Pole. And it also studied while it was descending in a spin mode with its camera and other detectors, that it measured the lunar exospheric noble gases while it was descending, and the first direct detection of the lunar exospheric water vapor. And this is very, very important measurement which was achieved at a very substantially low cost. I think all of us must be very proud of such a mission that has been conceived very first time and executed flawlessly. Now the Chandrayaan 3 also made very close to it a landing. And of course Chandrayaan 2 is also lying there, of course, not produced any result out of it, but all at the near to the South Pole, of course. Now looking at the Chandrayaan 1 on the lunar surface, we had many hypotheses to start with during the Chandrayaan 1 time. Of course, this has been improved upon or revised based on the observation of the Chandrayaan 1. Some of them I would like to discuss are the following, and if you look at the table, you will see before the Chandrayaan 1 mission, we were thinking moon is bone dry, but then the presence of the water molecules detection that happened with this Chandrayaan 1 has changed the way in which the entire science community looked at the lunar exploration. And we thought that moon is geologically very dead billions of years ago, and we now realize that it has a lot of volcanic or other geotechnically active system there. And we believed that the regolith absorbs the entire solar wind's proton. Today we know that it is being reflected back as an energetic neutral hydrogen atom, which is very important finding. And the lunar wake, which is very important measurement again, and it was devoid of the solar influence. That was the thought. And today we know it is the different population ions in the lunar wake has been discovered. And believed that being a very vulnerable place in the absence of atmosphere, moon is something that you can never go and settle there. But today we know that there are potential sites on the moon where future human habitation can actually happen, such as the buried lava tubes. So some of these findings from Chandrayaan 1 to 2 can be stated to be a trigger for further interest in coming out of the moon missions, and we have a resurgence of moon exploration across the globe. I think that has been very evident by the ferocity at which the landing has been happening in the recent times from Japan, from China, from USA, and many other players. And it is something great to happen, especially with the Artemis program of the US focused on the moon as the base for future expansion of other planetary system. And Chandrayaan 2 mission, which was one done during the 2009, and that whole of this is going to continue in various ways with the goal of chemical, mineralogical and geological mapping of the moon being the primary goal of it. And this extended the science from the Chandrayaan 1 with its payload capability, instrument capability being enhanced, and of course with a better observation capability. And today we know that the orbiter has been functioning very, very well. It is still continuing to function. Of course, the lander and rover could not accomplish its intended goals due to the landing anomaly. And when we look at from Chandrayaan 1 to Chandrayaan 2, there has been a lot of improvements in terms of the instruments, especially to support the science. I think this is something which is very, very crucial for us in the domain of scientific observations, how to build better scientific instruments. I think I don't have to speak about it. I am sure that you have a session look at it, how to build better scientific instruments in India. And recently when we were reviewing some of the Chandrayaan-3 instruments with our experts from others, they were really very happy about looking at our instruments and the quality of the instruments, the way in which we have built. I think many of those Western people were very happy and very surprised to see the type of quality of the instruments. I think we need to work on this still for future. But just look at some of these numbers. If you look at the capability that we had during Chandrayaan-2 to Chandrayaan-3, there has been significant improvements in terms of the spectral capability, the new bands that have been introduced, and also the extended boundaries of observations in X-rays, also the resolutions, cadence, and also the mass reduction or the compactness that you achieved, and also the capability that you have put in terms of the measurement boundaries, and also the new capability that you have built into payloads. I think all these are very significant in terms of science goals that you want to ultimately achieve from the observation platforms. And of course that optical observation always very, very important. A high resolution observation has been very important, especially when you look at the moon. And some of the sharpest and the high resolution images that ever been produced is by the OHRC camera on Chandrayaan-2. Today we have 25 centimeter resolution images of most of the moon. And because of that, we could, the Chandrayaan-3 could load those images for our hazard avoidance maneuvers that you have been done in the vaster area that you have been identified for this landing for Chandrayaan-3. This could be done because of the availability of high resolution images, which was not there during Chandrayaan-2 time frame. So it is something very unique today, and the satellite Chandrayaan-2 has done so much of imaging, and we have huge wealth of high resolution data which you should use for the future, for various future observations, including the missions that you are going to take place in the future, including the human landing on the moon and various other scientific activities that are going to take place in the coming decade. Now, if you look at the accomplishment of Chandrayaan-2 mission in a general way we can look at from various headings like this in terms of the hydration, the presence of water, looking at the surface, about the texture, the geology, the surface nature, the digital elevation, all of this has been better mapped. And also looking at the elemental composition, looking at the minerals using the instruments, the neutral ion exosphere measurements, and also related to the solar and heliophysic observations has been the outcome, essentially the outcome out of the Chandrayaan-2. And all of this are remote sensing observations. The in situ measurements did not happen. I think all these instruments have done exceedingly well, and all the data is actually at the disposal of the science community today. And some of the instruments in Chandrayaan-3 are worth noting. I think all of you know that we had 3 major instruments on board Chandrayaan-3. We had 2 such instruments on the rover, 3 on the lander and 2 on the rover, in addition to the shape payload on the propulsion module, the orbiter. I think this was what that has been launched in Chandrayaan-3, because Chandrayaan-2 is already having those instruments working very well. So there was no repetition of those instruments on board Chandrayaan-3, primarily to ruggedize the lander with more propulsion, more redundancies, more structural strength. Its mass has been increased by almost 200 kilogram plus. So all those capabilities of the orbiter was moved to the lander. So we had the similar suite of instruments on board the Chandrayaan-3. ILSA, which is the seismicity measurement, which is nothing but an accelerometer, triaxial accelerometer package, which was deployed on the surface of the moon to measure the seismic activity and other movements that are occurring. The chaste, which is a thermophysical property of the regolith, by actually drilling into the regolith and doing a measurement on the temperature, thermal characteristics and thermophysical characteristics of the regolith. The Langmuir probe, which measures the near lunar surface plasma environment by its deployment. And of course the lunar reflector array, which is provided by NASA, which recently you knew that they have done the location laser ranging from that point. And on the land, on the rover, the Prudent rover, we had two important instruments, the alpha particle X-ray spectrometer, which is APEX, and also the laser-induced breakdown spectrometer, both basically looking at the measurement of elemental composition, one using the laser ablation, other using the alpha particle impingement, and both have been able to do the measurement at multiple locations. The rover has made a substantial detour on the surface of the moon, almost 100 meters, so it could do measurements at multiple locations. That is really wonderful to see that, to have so much of data from, though 100 meters is not a vast domain of measurements, but I think we have substantial data coming out of this rover measurements that has been done. Now, if you look at the Chandrayaan-2 and Chandrayaan-3 in situ measurements, which Chandrayaan-2 of course was remote sensing measurements, and we had the corresponding in situ measurements. I think that type of complementary observations are very important for you people to look at. The Rambha, the APEX, the ILSA and the Chaste has really complemented some of the remote sensing observations. And I believe that the science that are likely to come out of the Chandrayaan-3 will definitely make use of both these observations from Chandrayaan-2 as well as Chandrayaan-3 in a complementary basis, and you should be able to bring out better outcome, because we have two beautiful instruments working now. Chandrayaan-2 is still functional, Chandrayaan-3 has enough data, which is in situ measurements. I think this is something very uniquely placed data set that should be useful for the entire science community. Now, looking at the landing sites, I think all of us know that historically the landing sites have been in the more close to the equator to start with, and some of them ventured into the South Pole as well, or even on the dark side of the moon or the back side or the invisible side of the moon. But there were reasons for scientific inquiry as well as technological complexity on looking at where we should go and land. I think all of us know the southern side is more challenging in terms of the surface characteristics, the lack of solar energy, but it has more of scientific value, especially from coming at the unique position where the sun illumination being very lower, and has a special way that we could specifically look at from the scientific interest, especially when the topology, the mineralogy, etc. But it has more challenges. I think that's why there is an interest in going to the southern side. And all of you know that many of those missions that have happened recently are all focused on the southern pole or closer to that. But it has become a very complex mission, unlike the one which was done in the past on going and landing on so many places the both Americans and Russians have done. Those missions were more focused on more equatorial or closer places, especially, and even Chang has gone to the northern side earlier. So we would like to continue on this future missions more focused on such areas, not into the equator. Unless we have a human launch that has to happen more for safety purpose, we may possibly do it more closer to the equator to start with. Possibly we'll move towards other places much later. Now, Chandrayaan-3, I think this is something that we achieved in the recent times. I think all of us should be very, very proud of this achievement, because this mission was very uniquely placed after the debacle that we had during Chandrayaan-2 of not able to make the soft landing. Making a soft landing after 4 years of hard work. I think this, we must thank the entire community that worked to make it happen, especially to decipher what went wrong in the mission. It has not been an easy task to identify exactly what actually went wrong, but I can tell you even what went wrong was not revealed even in the first year. I can tell you that it was actually revealed after the third year of the work. The real cause of the mission, the problem, was actually shown up in a very strange random experiment that it came out, one of the anomaly. I think if you had not corrected that, it would have caused problem in Chandrayaan-3. This is the type of challenge that we have in a mission like this, because we have not getting the hardware which has failed back home to do analysis. We only know the data that has come out of the telemetry, and also the hypotheses that we have, what could have gone wrong. And many things can go wrong in such a mission, and which is not revealed in front of you from the data sets, because we don't do so much of measurements to support your the mission, because we have an acute shortage of telemetry data power. So everything is not measured. So for example, the anomaly that we had in the software, some of the algorithms, some of the boundaries that we have set there were also physical anomalies in the system. I think all this could be come out through extended work of people, and we were able to correct them. I think we should be actually very proud and also lucky. I think in this time mission, little bit of luck also helps us. When you work hard to achieve something, luck also favors you in some manner. So we had a very lucky mission. We must tell you that the launcher put it at the right orbit, and this time it did not go to a extended orbit. Then the fuels were well preserved because there were no propulsion anomalies. So we had a lot of fuel left out, both in the orbiter or the propulsion module as well as the lander. And even when we had little bit of anomalies in instruments, we were able to land using rest of the instruments very safely. And we did not end up with any contingency options even in the guidance algorithm that we have set for it. I think all of this went very well for us to make a very precise and soft landing with a velocity which is actually lower than our nominal that we set. I think this is very exceedingly good as far as the overall guidance and algorithm, the propulsion, everything is concerned. Gives us a lot of confidence to take up such missions in the future. And not only that, it actually landed safely. Subsequent to the landing, we had the deployment of the ramp, the rover coming out. It's moving around on the moon, deploying all the instruments, especially the one which actually want to get into the regolith, it has to drill it. In fact, I must tell you that when we drilled one time, we had a break of this, that tip, which actually goes to sand in the laboratory conditions. And we must be lucky that at that point there was no rock, that it didn't hit that and broken it tip. Many things have to happen to our advantage, that the whole mission has gone very well. Even ILSA was deployed very safely. Both deployment of the REMPA payload and also the Apex payload on the rover happened very precisely. And we also landed at the right day so that the 14 days of mission could be done with the solar power available. I think all these are very, very important. We did not change even the launch date. We exactly landed at the targeted date and time. I think it's really wonderful to see this mission happen exactly like this, and 4 years of hard work. And those people who have been responsible for it, I think one of the person is sitting here, our Kiran Kumar sir, who has been spending so much of sleepless day and night along with the designers to make sure that everything is done right. I think with this clearance only the entire mission went through in the last phase of it, and also the operational phase of the 14 days. So we had a perfect landing, experiments and measurements. But the most important part and beautiful part of it is that we extended the scope of the mission little longer, little more, like the hop, the jumping that we did on board. Though it was a short, small jump, but it was a great jump as far as we are concerned, because a confidence that we got it by the small jump is tremendous. That we can one day take off from the moon and come back to Earth. I think it has been proven by the jump of the rover as well, lander, as well as the orbital module, the propulsion module being brought back to Earth. I must tell you that there were a lot of worries to start with doing it, reprogramming the whole lander for such an operation. There were a lot of worries. And even bringing back the propulsion module back home, we had 100 kilogram propellant. We knew that it is not enough for doing it. Still we tried it, and we made it due to various algorithms that came out, the numerous mathematical process that went into the making that mission simulation possible. All this add confidence to the next set of designs that we are trying to do in Moon. I think the accomplishment of Chandrayaan-3 is something unparalleled in the history of our technological capability in terms of missions like this. I believe the same thing will happen from the scientific instruments that we have done, the type of measurements and data. Let us wait for that day that some unique finding that has never been published will come out of your team. I think I am waiting for it. I am very impatient about it. I think I must tell you at this moment. Now, Chandrayaan-3, as I mentioned earlier, the original mission has been extended in various ways. As I mentioned about the hope, the bringing back from orbit of the moon back to the Earth orbit, the travel of the the rover over a long distances, avoiding obstacles and planning its path. And beautifully is that we were able to capture beautiful images. Nobody would have believed that if the rover did not take the lander photo. We have only one photo till now, not many. But that is a beautiful photo. Today, a very historic photo of that black and white photo that we have, the Vikram landed on the moon with his 4 legs intact. Not one, it's not tipped over yet. So unlike the many others. And also the rover coming down on the ramp has beautifully been captured, and also it making a turn, almost 360-degree turn, has also been captured by video cameras that has been put on the Vikram. So even you know that the booms that the ILSA which we are deployed, we were able to put back, redeploy, and then do the hop, and then once again deploy it. So all this we did, which was never thought about first time. I think all this goes to the confidence of the team that when did the Chandrayaan 2. Today I can see when they are looking at the future moon missions, the confidence level is exceedingly high, and the type of architecture they are bringing out is really fantastic. I will discuss it a little later. Now, if you look at the results of those experiments, I must admit that I am not an expert in this. I think some of you may be greater experts to explain this, but this is something which is understood by common people. So that's probably one thing which I want to discuss, but some of them from both the mineral exploration point of view, mineral mapping point of view, these both instruments, both the alpha particle X-ray spectroscopy as well as a laser-induced breakdown spectroscope has identified elemental compositions. Here the only new thing that has come out is abundance of the sulfur that has been detected, which has been very clearly brought out, but many others are well known from the remote sensing basis itself. These were well identified, but there we are looking for maybe more scientific outcome out of this. Similarly, the REMBA has observed some of the pattern of the temporal variation on the surface, which is contrary to what we believed. And similarly, the Chaste has also found out measurements, which again surprisingly different than what we thought about in terms of the thermal isolation characteristics of the regolith, which showed a substantial higher temperature difference between the surface and the deeper measurement. So these were some of the measurements which were found to be different than what we initially thought about. I think these are uniquely placed in terms of observation on the moon science. We also had observation from the ILSA, the accelerometer package. Some of them could be due to the physical activity that were taking place there, and some of them could be due to the activity that are taking within the moon. I think these are to be deciphered separately, and then we should be able to make some good model out of what is happening there. We would have been happier that we had a long-term observation. We have only just for 13-14 days of observation, and this hopefully this has some hidden information that you should be able to decipher. Possibly with a single instrument it is not easy, I understand, but in the future we may be able to do a better measurement in this area. Even the shape payload, after its observation for about a few months, about 2 months, we have a good set of data, because this is going to be a consistent data, so we didn't want this to be kept for a long time. But once the propulsion module moved from moon orbit to earth orbit, the ability of this instrument to look at earth came down, but it is just sufficient enough even today. So we found that the type of spectral characteristic for a planet which has water, carbon dioxide, oxygen, etc. in the atmosphere as well as in the surface, and also the absorption lines related to them are very, very clearly shown here. But this is something very useful for when you observe an exosolar planet and then make a spectral characteristic of its atmosphere through the light that is passing through the atmosphere of those exosolar planets. Then we should be able to make an identification of a habitability of a planet. I hope that this instrument will give some clue to that. But this data is now available for you to do the study and further make models out of it. Now let me jump further to the Aditya L1 mission, and this is again a very complex mission which has been going on for last some 8-9 years, and the work on this has been going for long periods, because the 7 instruments on board, this has been one of the very challenging optical observatory capability instruments. And more than that, the development, calibration, testing to the satisfaction has been a big challenge. I am very happy that we could ultimately solve most of the problem and reach the launching condition. And today we know that all the instruments are working beautifully. The mission has achieved its goal of traveling 15 million kilometers distance from Earth to the Lagrangian point. We were able to plan very unique mission approach of moving the satellite from Earth orbit to the Lagrangian point and through a very unique path of trajectory which is optimizing its fuel, and it entered precisely at the same time, and today we have the halo orbit of the L1, and with its instruments now being tested, calibrated to and ensured successful operation. So as far as we are concerned, the mission engineering goals are fully accomplished, but now what we are looking for is the observation that has to happen in the next 4 or 5 years. With the remaining fuel in the satellite as well as the type of health of the satellite, I believe that they will be able to do significant observations to support the heliophysics data. So look at the instruments on board Aditya L1. We have 7 instruments, and 4 of them carry out the remote sensing observations of the sun, and some of them do the measurements of the particles, both the solar wind particle, the plasma analyzer package look at the particles at the heavier ions as well as electrons, and we have the magnetic field measurements using a triaxial high resolution digital magnetometer. So the bigger instrument is a VELC, which is a corona imaging as well as spectroscopy capability. Then the suite, which is an ultraviolet detector, low energy and high energy X-ray spectrometers. So such a suite of instruments has not been put in any solar spacecraft observatory till now. So that's the beauty of this. So we have correlated measurements from the imaging to the magnetic observation. So this is something which is going to be very unique as far as Aditya L1 is concerned. So the instruments were placed in the satellite at very good engineered satellite within the payload capability and mass that we could have this mission accomplished using the PSLV rocket itself. So I must say that it has been a fantastic working of ISRO with the various other stakeholders like IAA, IUCA, and many other institutions that are partners in other instruments. We were not only doing this instruments development during this time, we were also working with the scientific community to make use of this data for our research purpose in the future. So we were building the science community around Aditya L1 in the pre to the launch, and we should continue to do this in the post-launch scenario as well. So if you look at the goals and uniqueness of Aditya L1, basically we are looking at the dynamic events on the sun, basically the solar atmosphere, the photosphere, the chromosphere, and the corona, and then spectroscopic diagnostic of the coronal plasma during the quiet as well as active phases, in situ measurements of the particles that I mentioned, both magnetic and particle measurements. And this is very important because we have a certain uniqueness like this, that we have a CME dynamics which is very close to the disks, like the 1.05, and this provides information on the acceleration regime which is not observed very consistently, and the magnetic field and topology of the active regions are measured, and it will help us in terms of modeling of the CMEs and the flyers in the long term. And of course it observes the solar winds, its electron, proton, the alpha particles, its fluxes, and also its directional information, and also will have the flags and counts information through telemetry for early warning and information related to the space weather. Right? It's equally important. I think today we have one of the very active the solar activity right now happening. I believe the Aditya L1 should have been fully operational by this time really. And I don't want to explain this, how it has been inserted in Aditya L1 in the halo orbit. I think it's already been published sufficiently, so I will quickly go to some of the observations in the X-ray measurements that have happened in both from the SOLAX as well as the Helios. It shows that the X-ray proton count changed with the time. Sudden increase has been observed with the flares, and multiple flares have been recently observed. Similarly, the Helios also observed the high energy X-ray emission with the sudden increase on the count, which is coinciding with the flares. I think these observations corroborate some of the hypotheses of the particle measurements. We also had a measurement on the solar wind ions, primary photons, and alpha particles, as has been recorded by the aspects. And similarly, the time series representation solar wind electrons was been observed by the PAPA payload also. And similarly, the interplanetary magnetic field also observed from other satellites have been recorded in this curve. This is about the interplanetary magnetic field measurements, both the 3 directions. And this also captured the imagination of the community. The suit images in various spectral bands has been displayed as beautiful color images of the sun. I think this has also been very well captured by the public. I mentioned about this, public also got enthused by the outcome of Aditya L1 greatly. Now let me quickly go to the other mission, which is the ExpoSat, which is again a unique mission. We have been waiting for this launch for quite some time. And on 1st of January, the new year beginning, we had the launch of the PSLV with ExpoSat. And it has two important instruments, the X-ray polarimeter satellite instrument, which, POLIX, and the X-ray spectroscopy and timing expects also. So this is basically to look at the polarization information of the medium energy X-rays, as well as long-term spectral timing studies on soft X-rays for bright X-ray sources coming primarily from black holes and other objects. And these two instruments, POLIX and EXPEX, are very interesting instruments. And we are going to look at some of the well-known bodies. About 50 of the X-ray sources will be a systematic manner. This will be observed. And these instruments have been realized by the Raman Research Institute as well as the UR Satellite Center. And I believe this is also something which we are looking for in the days to come for substantial scientific outcome. And some of the initial observation by these payloads, both POLIX and EXPEX, are shown here. And there's some of the Crab pulsars have been detected with the scattered X-rays. This is from the POLIX team. And similarly, the EXPEC looked at the supernova remnant of the Cassiopeia, and then it produced the identification of these elemental identification signatures have been observed from this payload during this well-known supernova remnant. Now let me quickly go to some of the ongoing discussions or plans for future scientific missions. I think this is something which is very important for all of you to think and plan what all possibilities are there and what more we need to do. When we looked at Chandrayaan, beyond Chandrayaan 3, many things come to our mind, whether we should repeat such a mission or we should bring samples or we'll do a type of mission what is going to be different than what others did. I think this question is still being debated, discussed. Currently we are working on a concept by which that we should be able to go there, land, collect sample of various nature, bring back to Earth, and then hand it over for further physical studies. So an architecture around the current knowledge and skill of the rocket people as well as satellite people have been worked out, and the scientific goals are to be fully separated out now. We have to discuss in greater detail. Kiran Kumar sir is involved in this work and many other people. So currently we have looked at the architecture of it, and today it is possible for us to do it with our current launch vehicles, maybe PSLV and maybe GSLV Mark III. But it's going to be extremely challenging, I must tell you. It's not like even Chandrayaan 2 or even 3. We have to have multiple missions, not one launch, multiple launches. And we must have docking capability either on Earth orbit or even Moon orbit. And we must have robotic capability to operate, drill and select sample and load it into compartments which will be keeping this samples very safe. I think some of the missions earlier they sent for sample collection. When they collected sample and came back, there were nothing left in that. It failed to collect and retain it internally. So there are a lot of challenges in such missions. Even a docking failure can cause the entire mission to fail. So a lot of new things are to be developed while we want to do this. So let me look at this community from the science point of view. Of course, we have identified this as a possibility, a technical possibility to do this mission, because we first started with remote sensing, then we looked at in situ observations. Now third phase, we want to bring the sample here for greater laboratory observation and analysis. What more we can do? What more we need to do? I think this is something very important. I look at you for coming out with ideas and discuss in the Apex Science Forum for us to incorporate in this mission. And I can tell you this mission has to be accomplished in 2027. And we would like to do this using the current capability. So let us all work together to make sure that another Chandrayaan mission will happen in such an architecture. Currently a discussion is going on between ISRO and JAXA for a lunar lander mission, especially in a very shadowed region on the South Pole. And this mission is not yet approved. We'll have to go through the processes. Here the launcher will be from Japan, the rover also could be Japanese rover, and the lander will be an Indian lander. And so instruments, we can put it either on the lander as well as on the rover. So we will have to look at through the joint research working group, what all things we can do such and such a mission. This is yet being evolved, and currently we have a certain amount of architecture of how to do this using our payload capability. Other missions that we are currently discussing are Venus. I think this has been going on for some time. Various architectures of Venus mission has been worked out. I think all of you know the interest in Venus. I don't have to explain to you why Venus is so important and interesting for us to do the mission. Looking at its atmosphere, its surface topography, the dust, the volcanization, the huge clouds and lightning that is happening, the acid atmosphere. I think all of these are worth exploring. Similarly, is a possibility of landing on the Mars. Today we know the helicopter which was sent is now silent. So possibly some of our people were speaking out that we are going to send a helicopter. I don't know. Maybe we will find out whether we should be in a position to send a helicopter by ourselves. But then a mission to Mars for landing has a very, very good possibility, and we should do the full configuration study and mission study while look at the science side also, what exactly we want to accomplish through this mission than what we did for the MOM. So this is currently under discussion, and again it will go with the launcher capability because mass and mission possibilities limit us from making a heavy lander. This mission, we call it Disha H&L, a dual aeronomy mission, which is again under study. I must tell you, this has not made huge progress yet. This is a mission to look at the disturbed and quiet time ionosphere thermosphere system at high altitude, putting two spacecrafts orthogonally to each other, near orthogonally at two planes, and look at the solar forcing, the radiation, the solar winds and fields, and coronal mass ejections from two planes, and look at the understanding between the physics of the Sun-Earth system connection. I think this discussion has been going on, but we have not reached a very firm conclusion on the architecture of such a satellite, the mission possibility, etc. This work need to be done in the coming days to finalize this. Yet another mission that I have been hearing quite a lot, but not work progress so far, is the ExoWorlds, which is nothing but a telescope of 1.7 meter, and also with spectrometers in near ultraviolet, visible and IR spectral range for very high photometric precision, basically to look at the atmosphere of the exosolar planets and make certain measurements related to the chemical abundance, equilibrium process, non-equilibrium process, the habitability, etc., etc. So this will be a very important mission, which is very unique, but the challenge is building this and engineering this of this type of telescope continue to be a major challenge. I think we need to close the boundaries of the design mission specification, reach to a mission definition. I think in the coming days we should be doing it, and I am very sure this is very, very important mission, and we need to find out good science team to make measurements out of it, and it should not be limited to a few people. I think this is something which is currently constraining us. Another interesting mission that has come out with a proposal from IIT Mumbai is the Daksha, an Indian sky on transient skies, which looks at the low energy detectors, which is placed at 13 different locations, and similarly the medium and high energy band detectors, basically to look at the powerful cosmic events like the gamma ray burst as well as other electromagnetic counterparts of the gravitational waves to observe on a continuous manner. And this will definitely give a greater idea of the current interest, topical interest in the this domain, and a very good design document has come out, and we should be able to analyze it and look at the user community in this. Here again I would like to tell you the user community is very, very narrow and very limited, and we should look at how we can expand this user community across institutions who have an interest in this domain. So this is something which I am looking forward before we take up this mission in a serious manner to build it. Today we have a vision given by our Honorable Prime Minister. I think all of you have heard about it, read about it. In the recent 2020 we had a space sector reform, and after all this success that you have achieved through in the missions, I think there is greater emphasis on science from space, science of space, and science at space. So if you have to have all of this, we need to have a different approach today, which is nothing but the long-term vision of space. Like human access to space must be enhanced substantially, and we must have a space station. We call it Bharatiya Antariksha Station, which should be placed in the orbit by 2028, the first module, and the full module should be completed by 2035, which has a capability to have human habitation, stay for longer duration, and we need new rockets. The NGLV has been architecture has been done primarily to support human space flight with a large number of crews for continued missions to such locations. And we should also have a lot of science coming out of such a possibility. It's like an ability to go to microgravity and conduct experiments. Today we know ISS is flooded with experiments. Every day they conduct tons of experiments from industries, institutions, laboratories, in various places, and it has a potential to bring out new technologies, new science, new commercial use in various domains. For you look at material science, look at drug discovery, additive manufacturing, and many domains. They have science and technological development happening there. So we must also create a technology science roadmap for zero gravity environment in space. I think this is again another competence that we need to develop in the Indian science community. I think this is also not grown too big, because when we looked at the type of experiments we want to do in the Gaganyaan mission, at least 5 of them have been now shortlisted. They are not very exciting missions or exciting experiments for me. Maybe some of you may be primarily doing the first time doing it, but what is important for us is to find out very unique science experiments that we can do in a human space flight in a zero gravity environment. And this is very important. I think let us look at how to create this ecosystem which will work on zero gravity science, human interacted science, let it be in biological sciences, let it be in medicine discovery, let it be in material sciences, where there is an interaction is required and measurements are required at a low gravity conditions. So we need to create human-centric laboratories and associate technology, and we will be very happy to create that in ISRO for your case if you have a core interest. And we are also looking at, along with this mission, we must have an expanded capability for moon mission. I just discussed about the next moon mission, but it's not going to be ending with one moon mission. We must have a continuous access to moon as well. And finally, what we want to have is a human landing, an Indian landing on the moon by 2040. It won't happen just by an accident. It won't happen by one development. It will happen by a continuous exercise of missions to moon, and then expanding knowledge on moon in a substantial manner. Only then it will be possible to have a human mission from India to moon. Otherwise, it is not possible. So I am looking at how to create the narrative for moon mission and how to create scientific goals for people going to moon and then bringing some tangible benefits out of it. I think it's equally important. Unless we create it, nobody will be supporting us with the type of money that is required to do such a mission. I think it's not going to be a low-cost exercise at all. Sending humans to moon, because we need to develop huge launcher capability, the type of laboratories and simulation systems that we need to do. And it cannot be done just for once. It needs to be done for multiple times. And all this must be well understood in the context of others doing it, because many other nations are also going to moon. I think the renewed interest in US, that in China and various other nations. So this aspect must be taken care, and we need to create the type of scientific talent and pool in this country to support this idea. I think these ideas are already there. It is a vision of the government to do it. So we need to prepare ourselves to find out the right type of use and outcome out of it. Let me tell you that this will happen only if you engage with various institutions of this country. Today, we have a lot of academic partners, communities across this country in various ways. We do engage with all of them through sponsored research. We call it RESPOND. Regional academic centers called RACs, Space Technology Incubation Centers, STICs, Space Technology cells in reputed institutions, innovation centers. We have ISRO chairs. We have centers of excellence and also many other centers of excellence that we are planning to create in the future. So all of this we do, but today the engagement, I cannot say it is very, very big as far as the funding is concerned. They are continue to remain low. And we should address this issue in a big manner. How to really enhance the research support from Department of Space? How do we really bring out more outcome out of it? How do we strengthen it? This is one topic currently I am engaged in discussion. And we are trying to find out from the conventional how to do little more in this area to create the type of people, talent in this domain. See, similarly we do with continue to engage with the space science community through workshops, data utilization exercises, user meets, etc. This is a continuous process. Those who are not part of it, I think I invite those young people to come and then participate in this such exercises whenever you are coming to know about it. This will give a little bit of exposure how to access the data that we have and make some research outcome out of it through your academic collaboration. We have a huge amount of science data at ISSDC, and this is meant for you people, those scientists who wish to make use of the science data that comes out of all these missions, and it can be made available. Only you need to contact Mr. T.P. Das, who came just before me, to connect to the data center and access this data for your research. I think there are committees in ISRO who will encourage you to make use of this data and enable you to make use of this data. Another interesting capability that we have is the missions to space through upper stages of PSLV. We have created a platform called POEM, PSLV Orbital Experiment Module. The upper stage of PSLV is now converted to a satellite with solar panels, with batteries, with computers, with control system. It stays there for a few months and it can do a lot of exercises, lot of experiments. And those who want to build experiments, you don't have to build a satellite. You need to build only that experiment. The power, the telemetry, the data, communication, commanding, everything, the POEM will do. So the complexity of the mission comes down. It stays with that and then it will give out the data for short-term measurements. I think many people have come forward to do such experiments. And we are making the stage more and more better with every launch. Now, very precise attitude, hold control capabilities, orientation capabilities to sun and earth, all these have been built into this stage for longer duration of stay in orbit also. So this is again an invite to those scientists who would like to work on ideas at very extremely low cost. You should be able to access possibly a free ride as well. So this is something that you must make use of it while you are working on technologies. So we can look at microgravity experiments, and we are planning in the coming POEM robotic and smart space robot technology demonstrations, rendezvous and docking type of experiments, small satellite technology development, laser communication technology development. All these are happening within ISRO now, and we would like to put them on board and experiment them. And this is again a collaboration possibility in all of this, or even more with the upper stages. I think we should not also forget about the opportunity that is given to science community using the sounding rockets. Every month we launch a sounding rocket from Tumba. And this is continuing as a tradition of sounding the atmosphere, getting the atmospheric parameters, and this goes into our database because we would like to build thousands of rocket launches in the database that goes into the atmospheric model creation. Today we have a beautiful atmospheric model based on the data that has come out of sounding rockets. But we would like to make use of more instrumented launches when science community wants to build some instruments and put it in the upper atmosphere and do measurements. And we will be very happy to support such experiments even in the coming days. But this has come down in the last tens of years, and there are no takers for it. I think this is something very worrying to me, that there are no, the initial euphoria that we had in sounding of atmosphere and measurements are no longer there today. I think with this, we must rekindle this in the academic institutions. Similarly, the other, the astronomy-related proposal, which IAA is leading, the Internet Spectroscopy and Imaging Space Telescope, measurements, etc., is also going to support the future scientific goals of the ISRO, complementing the space-based observations. Another area is the student satellite that we have been working to promote the space technology, science, etc. And today we have an ecosystem helping you to build satellites, ground stations for your work. I think this is going on well. Recently we have launched some student satellites. Some of them are part of the POEM experiment itself. And we can also support you as an institution to build space stations and create that capability to download data. And we have a new entity called InSpace, which will mentor you, which will help you to get the technical support and facilities from ISRO to develop, build, qualify for flight. All of these are now possible for startups to test their ideas. Some of the startups today are in the space sector, started like doing small experiments on POEM, then came and built the small satellites. Today they are growing in various domains. I think this is again an open invitation to budding entrepreneurs who are here in the part of this science community who would like to identify some science objective, take it to a level of commercialization later through space-based instruments. So I am just looking at some of the possibilities that they have done. Some of them have done conjunction assessment, debris management, maneuverability, interference analysis. All this we have supported them. Yet another area is the response basket. We have been announcing it every year. The new response basket has been announced. I believe some of the institutions have already, who are present here would have already responded with the offers of participating in it. But the relevance of this topic, as well as the keen interest and competence of the research faculty and students, will be the measure by which we will be selecting it. And we will continue to engage in this response activity. Primarily, this is basically an engagement with the academic community and researchers with ISRO. I think all of you are familiar. I don't want to spend more time on it. Another activity has been a funded RACs, which is basically to pursue advanced research and in the area of space and act as a facilitator for the promotion of space technology activity. And we have created regional academic centers in following areas as shown in the map. And this, some of them do very well, some of them not doing that well. And we are having a serious review of the outcome of RACs today, and also looking at how to create RACs in the new emerging institutions, including private institutions in this country, to support this program in the coming days. Similarly, the space technology incubation centers, we look at centers where private startups can come and then get engaged. So space related startups can be incubated at these places with the mentorship of these institutions. And here also I must tell you, some of them are doing exceedingly well, some of them not doing very well. So all of them are not at the same level. But the goals of the STIC remain same, and we would like to review and then make it strengthened in the coming days. And space technology cells have been established many years back, primarily in the IITs, IIScs, to help engage with the faculty there in the space research, and also the students from ISRO go there and do research along with the faculty. So this has been recently going on, and we are looking at how to enhance the funding. Recently we have taken a decision to fund all the STCs, greater funds, higher percentages. It's almost 50% increase in the overall allocated funds. All STCs have happened this year, and we look forward to see very useful research collaboration with IITs through this program. And we also conduct various programs for students. One of them is called Space Science and Technology Awareness Training Program. And this training program is addressed through lecture modules. You can look at the overall, for example, overview of space science and exploration and various lectures that are available for students. And this you can take and then participate and get a certified after conducting a small examination, online test. And after that, you students could get a certificate out of the ISRO after participation of such programs. And we are planning to put more and more online material on it to help people to understand space science and technology. All of you know about InSpace. I believe the authorizer, the promoter of the space technology and autonomous body to support the non-governmental entities to come up in space sector. There you use it as a single window mechanism for approaching those who are interested to work in space sector as an entrepreneur who want to make use of the support of ISRO, or anyone in the space sector, through mentorship, through test facility utilization, through technology transfers, etc. So InSpace will enable all of this. They have a website, and you can go and register and find out what all things are possible with InSpace. So let me summarize my talk telling that the type of work we did in the space sector in the last many years, working along with the social national needs of space systems, we were able to do certain amount of science activities, building satellites for specifically for science goals, and then do certain amount of exploration. Though it has not been a larger budget share for our space program, but it has made such an impact today, especially with the success of Chandrayaan 3, the Aditya L1. I think the narrative has changed, that India is somebody to look upon as a nation with a capability to do science-based experiments, space-based experiments, and we should not lose this opportunity. I think this is something which I want to tell you. The confidence of the nation is very, very important when you look at such missions. And if you go with such a mission, as I mentioned in my inaugural talk, this becomes very important. That narrative becomes very important. We cannot get rid of the narrative that the space is for the common man, for the nation to build. I think these are very important because there are a lot of services that we need to provide through the space technology. The launching capability, which is a strategic capability, we need to nurture and create. The satellite building capability is now moving into the private domain substantially. The application segment is becoming more industrialized, commercialized. But what is more important is the science side. The question happens that who is going to fund this science activities? And it has to be only public funding. And when you look at public funding, this challenge of these questions will always be lingering in our minds, in everybody's mind, all the public, those who are going to approve it. So all of us have to work together on this. The first and foremost thing what I have to tell you is that we must create a long-term roadmap for space program, especially the science program. What exactly the Indian contribution to space science? I think this is something which we need to create, envision. After that, we need to find out what all missions need to be done to meet this Indian space science vision. And which are the institutions that we need to participate. We should be made responsible to do a certain amount of work in this sector. And they must be tasked to do it through governmental funding. And we must look at a result-oriented approach in terms of the tasks that need to be done by each of those institutions. It must be complementary of Earth-based observations, space-based observation, simulation, computation, and creation of human capacity to do all of this. I think such a vision is something that we need to create. I tell you that at the end of this conference, if we can sit together and work out how all institutions of this country should come together to do this, it will be one of the greatest contribution of this conference, I believe. People like Kiran Kumar Sir is here, who has been heading our Apex Science Forum. He can be a mentor for all of you to help you to create it. But I look forward from the younger generation of people to create this roadmap. Your roadmap is more important because you are only going to take it up in the next tens of years to take it forward. So let me stop here and say a big thank you to give me an opportunity to speak about the work of each one of you. None of the work done are by you people. I think your results only I showed, and I had the privilege of showing it as the chairman of ISRO. But I want to demand something more from you. I think that demand has already been put in the beginning of this. What I want is to engage with the public in a big manner. It's very, very important because the public means the decision makers, ultimately the government, and they will listen to them. Suppose the country says that we are not doing enough in science, in space science, definitely this voice will be heard by the people who will contribute to this. And this will happen only if you educate the public, students, the aspiring people. They must say that I am not getting opportunity, I am not having enough of data. And that will change the narrative. It will change the thought process of the decision makers to invest more and more fund. Today, let us not worry that the nation is actually very growing nation. We have the resources to allocate for it. The only thing what we need is a confidence to do it. I think the confidence has already come with the type of missions that we have accomplished. And we need to force it a little better, little more, with a clearer roadmap and vision. And if you have that, I think we can make a significant impact in space science through our interventions in various sectors, like the capacity that you are developing for launches, the ability to build satellites in the sector, involvement of industry and academia in big manner, even in scientific goals. I think we don't think that scientific goals are an elite goal. It is not true. It can be even applied to technical organizations, industries. They look forward for something. Why don't you discuss with the drug makers or the vaccine people of this country to how do we really engage you in space sector? Why don't we conduct a brainstorming? What all possibilities exist? I think this must be done so as to create a very vibrant community around the space to work for it. I mentioned about the zero gravity environment studies. So These are the thought process that comes to me when you talk about what we did, but what we need to do are much bigger and much wider community need to be created. It's not only limited to those three domains, like you understand the interaction between Earth and the space, then we look at the space between the planets and the Earth, then we look at the planets and beyond. It's not that. It is, space science is something that connects all of us together. It is something that affects our life on Earth. It affects our day-to-day science. It affects our survival. I think all of these are very, very important. It affects agriculture. It affects the medical domain. It affects the material science that we want to discover. So I would like to conclude this, since Vice Chancellor has indicated. I think I would have overshot a little bit. So thank you so much, and look forward for your greater cooperation. Thank you.
Thank you, sir. I think it shows in your passion when you just can't stop speaking about it and we have to indicate that time is up. I'm sure the audience is absolutely on the moon today, having heard such an enthralling talk from you. To express our gratitude and thanks, I request our Honorable Vice Chancellor, Professor Harilal B. Menon, sir, to present a memento to our esteemed speaker for public lecture, Dr. S. Somnath. Thank you so much. A big thank you to all of you for being patient listeners for this public lecture by Dr. S. Somnath. We conclude the first half of NSSS 2024's first day here, and we will be proceeding for a lunch break